Most sources consider Noether's work in three distinct areas. From the time she finished her doctorate in 1907 until 1919, she looked mainly at differential and algebraic invariants. Then, between 1920 and 1926, she considered the theory of mathematical rings. Finally, between 1927 and her death in 1935, she looked at non-commutative algebra, linear transformations, and commutative number fields. We'll focus here on the work she did around the theory of mathematical rings. Before we look at Noether's work, a bit of history on rings and ideals is necessary. Commutative ring theory originated in algebraic number theory, algebraic geometry, and invariant theory. Kummer was one of the first mathematicians to work with ideals, and he did so in algebraic number theory. He discovered that he needed unique factorizations in trying to prove Fermat's last theorem. Dedekind also worked with rings in the late 1800s, but he only worked with them in a concrete setting, not in the abstract setting that you'll see Noether did. He was working to extend Kummer's ideas from earlier. Then Hilbert actually coined the term ring in 1897, but he was still working with a limited definition and again used a concrete setting. The first person to actually give the abstract definition was Fraenkel in 1914, but it went largely unnoticed and it did include some unneeded axioms. In 1921, Noether first published her definition of a ring. She said that a ring R is a system closed under two abstract operations, which we call addition and multiplication. 6 conditions must be satisfied. First, we need associativity of both addition and multiplication, as well as commutativity of addition and multiplication. It also has to be true that multiplication is distributive over addition, meaning that A times the quantity B plus C is equal to A times B plus A times C. And finally, for any A and B that belong to the ring, there must exist a unique element X such that A plus X equals B. Essentially there, we're looking for the 0 element. As we continue, we'll make use of the ring of integers z. We know that z satisfies these conditions and is a ring, so in a few of our examples we'll work using that assumption. In order to understand the idea of a Noetherian ring, we'll also need Noether's definition of an ideal. She said that an ideal of a ring R is a non-empty subset I such that if we have A and B that belong to the ideal, then 3 conditions are satisfied. First, A minus B must belong to the ideal, and the other 2 conditions state that R times A belongs to the ideal, as well as A times R belongs to the ideal, and that has to be true for any R in the original ring. This definition, as well as the previous definition of a ring, aren't exactly what we use today, but they are fairly modern definitions, and it's what we'll work with in the examples that follow. To illustrate the idea of an ideal, let's consider all multiples of 4 in the ring of integers z. It's often denoted as shown. Subtracting any 2 multiples of 4 is again going to result in a multiple of 4. For example, 16 minus 4 is 12, which is 4 times 3. As well, we can see that multiplying any multiple of 4 by another integer in the ring results in a multiple of 4 again. So negative 5 times 8, for example, is negative 40, which is 4 times negative 10. Let's consider a proof of the general case for the ring R. This proof holds not only in the integers z that we considered on the previous slide, but for any ring. Consider M1 and M2 that both belong to our ideal. If we take M1 times R minus M2 times R, we can rewrite that as the quantity M1 minus M2 times R. And we know then that this belongs to the set, since M1 minus M2 belongs to our original ring. So our first condition of an ideal is satisfied. Furthermore, we can take A belonging to the ring and B belonging to the set that we're considering. We know that B is equal to MR for some M in the ring, and therefore AB is equal to A times the quantity MR, and using our associative property for the ring, that's equal to the quantity AM times R. So for that reason, we can say that AB is equal to AM times R, which belongs to our set because AM belongs to the ring. And finally, since we have the commutative property, we know that AB is equal to BA, and therefore BA is also a part of that set. And at that point, we can say that the multiples of R is an ideal. Now we have the background that we need to understand the definition of a Noetherian ring. A ring R is said to be Noetherian if R satisfies the ascending chain condition on ideals. What that means is that every non-empty set of ideals in R has to have a maximal element, or that the chain must terminate. So more formally, we can say that given any chain I1 contained in I2 and so on, there must be a positive integer n so that in equals in plus 1 and so on. We're going to go back now to the ring of integers z and actually prove that that's a Noetherian ring. In order to do so, we're going to use the fact that all ideals in Z are of the form that we considered earlier, and they're called principal ideals. So if we consider the ideal I that consists of multiples of 4 and the ideal J that consists of multiples of 8, we can see fairly easily that J is contained in I, and that's true because any multiple of 8 is also a multiple of 4. If we look at the more general case, we can say that J is contained in I only when n is a multiple of m, or in other words, only when m divides n. Now looking at the more general chain, where we have ideal 1 contained in ideal 2 and so on, each of those ideals ij is multiples of an nj. So based on what we saw on the previous slide, we can say that n2 divides n1, n3 divides n2, nk plus 1 divides nk, and so on. One assumption that we're making here is that n2 is a proper divisor of n1, which means that n2 isn't equal to plus or minus 1 times n1, and that's true for each case that follows as well. So looking at absolute values, we can say that the absolute value of n1 is greater than the absolute value of n2, and so on. But this is where we reach a contradiction because there are only finitely many positive integers that are less than the absolute value of n1. So at this point, we can say that the integers are indeed a Noetherian ring. To compare, let's also consider an example of a non-Noetherian ring. If we consider the ring of polynomials Rx as the ring of polynomials over infinitely many variables in a non-zero ring, we can see that it does not satisfy the ascending chain condition. The sequence of ideals would be x1, then x1, x2, then x1, x2, and x3. And because we have infinitely many variables, that sequence of ideals has no maximal element, and because it doesn't satisfy the ascending chain condition, we can see that it's not a Noetherian ring. Now that we understand the definition of a ring that Noether provided and the idea of a Noetherian ring, we'll finish off just by discussing the importance of her work overall. One of the first contributions that she made was the definition of a ring, and as we've said, we use very similar definitions today of both a ring and an ideal. But more than the definition itself, it was the fact that she took an axiomatic, abstract approach that was important. And it was the starting point for much of the abstract algebra that followed. Secondly, her use of the ascending chain condition was very important. It had been used before, but in a more concrete setting. So the way that Noether used it more abstractly became a new tool for proving many results. As one example, Noether later used the ascending chain condition to prove that each ideal of a Noetherian ring is a finite intersection of irreducible ideals. I'll finish off with a couple of quotes that also get at the importance of her work. The first is from van der Waerden, and you may recall that he worked with Noether in 1924 at Göttingen, and what he said is all relations between numbers, functions, and operations become perspicuous, capable of generalization, and truly fruitful after being detached from specific examples and traced back to conceptual connections. So again, he's getting at the fact that the really important thing that Noether left us with was her abstract approach. And the final quote here is from Gerrit Birkhoff, who spoke in an article about the rise of abstract algebra. And when you hear him mention a Congress, he's speaking of the International Congress of Mathematicians. He said, if Emmy Noether could have been at the 1950 Congress, she would have felt very proud. Her concept of algebra had become central in contemporary mathematics, and it has continued to inspire algebraists ever since.